Welcome back to the fifth section of Chapter 5. In this section, we're going to work again with the indefinite integral, which is where we end up with our plus c, as opposed to the definite integral where we plug in the two values. So we won't have bounds today, but the indefinite integral is all about finding the antiderivative. So we're going to be finding the antiderivative of a lot of different equations. And in doing so, we're going to be using another technique, a new technique called U substitution. And U substitution is basically taking into account the chain rule. So when we had the derivative, we always had to make sure we chain ruled if it was appropriate, where we'd multiply by the derivative of the inside of the big function. Well, this is how we deal with it in the other direction. And so the first thing we're going to look at is we have a lot of integral formulas, and they're just backwards from the derivatives that we've taken. Some of them we've seen. We've seen the integral of a constant. We've seen the backwards power rule. And this works as long as a doesn't equal -1. If you have 1 over x, that does not go to the power rule. That goes to the natural log. E to the x, other constants to the x. We have trig. So these integrals seem kind of strange, but that's just the derivatives of our 6 trig functions. Remember that sine and cosine just go backwards of each other. The tangent and cotangent give us either cosecant squared or secant squared, and the secant and cosecant give us secant tangent and cosecant cotangent, which is what we see there. Some of these can be kind of tricky to remember, especially because we don't see them quite as often as we see some of these other integrals. And because it's a couple things multiplied together, it makes it just a little bit different. Other ones that are kind of tough to remember are the inverse trig integrals. Remember, we did inverse trig and it came out to be 1 over the square root of 1 minus x squared, or 1 over 1 plus x squared, or 1 over x times the square root of x squared minus 1. So there will be times when you'll get things when it might be just as simple as this. And people will be trying to use U substitution. That's not going to work. They're going to be trying all sorts of things when really you just have to think it's just inverse sine of x plus c. So knowing all of your basic trig or your basic integral formulas is going to be a very handy thing. It's going to help out a lot, just like knowing your derivatives helps out a lot for your derivatives. I would write these down. You could make flashcards of them going back and forth. So you could look at the derivative, oh, that's the integral, and vice versa. And you can pause this, get them written down, and then continue on as soon as you're ready. In addition to our integral formulas, we have a few properties that we saw a couple days ago. And these would be the derivative of the integral is just the function. It cancels itself out. We had bounds where we'd have to plug this number in, but in general, the derivative of the integral is just a function. If we're adding, we can split them up. And if we have a constant times a function, this constant can go to the outside so that we can see it there. And then you can just deal with the integral of the function. And so that allows us these allow us to deal with bigger things that might have something multiplied, a number multiplied, or the sum of a few things. So we have polynomials or polynomials plus trig and things like that. But how do we deal with it when we have something to a power times an x, or where we do have x's multiplied together? That's going to take u substitution. And so for u substitution, we're going to take the big unpleasant part and we're going to replace it with u. That way it's going to be an easier function to integrate. And then we deal with that, and we'll see how we deal with that. And this technique can be used with definite integrals as well. Again, definite integrals and indefinite integrals are the same, except that in definite integrals you plug in the top minus plug in the bottom. But finding the antiderivative is the same. So if we have an antiderivative or an integral that we have to find, we have x times x squared minus 13 to the fourth dx. A couple options here. One, you could multiply out the x squared minus 13 to the fourth. That's not x squared to the fourth minus 13 to the fourth. Don't be that guy. There'll be x squared minus 13 times x squared minus 13 times x squared minus 13 times x squared minus 13. And you would multiply that out and then multiply by the x to get x to the ninth minus, I'm not even going to finish that because I don't even want to know that. That's one way you could do it, but that can get unpleasant. In the past section, we had things like that where it was just squared. Hey, you can multiply that out pretty easily. That's not going to get to be too bad. But multiplying this out, not so fun. And it's only to the fourth. What if it was to the 17th? We would definitely not want to be multiplying that out. So here comes u substitution. For u substitution, we're going to take the big unpleasant thing. That would be the stuff inside the parentheses. And we're going to let that equal u, because then we'll have u to the fourth. I know the integral of something to the fourth. It's going to be something to the fifth, and then divide by the new exponent. It'll be 1/5 something to the fifth. So we're going to make that equal u. So let u equal x squared minus 13. And so we have u. Now we need to find what is the derivative of u. Du will equal x squared is 2x minus 13. That's constant, goes away. So 2x dx. We want to keep the dx because what we're going to do is we're going to go up here. We have 2x dx. Well, up here in our equation, we have an x. Sorry, I meant to change the color on that. We have an x dx that we can substitute in for. And so the x dx, here we have x dx, we have 2x dx. I don't want the 2. So we're going to move the 2 over to the other side using division. So 1/2 du equals x dx. And so we can plug that in for the x dx. We can plug in u for that. So we're going to end up with the antiderivative of u to the fourth times 1/2 du. The 1/2 can move to the front. We don't have to worry about that. That's what that property was about. The u to the fourth is going to be a u to the fifth, and then divide by the new exponent. The 1/2 again can be out in front, just kind of goes along. We'll multiply those to get 1/10. U to the fifth du, that's it, so that plus c. Now we don't want u to the fifth. We need to plug back in what u equals. U equaled x squared minus 13. So we have x squared minus 13 to the fifth plus c. So if we multiply this, or if we take the derivative, we'd multiply by the 5. 1/10 times 5 is 1/2 times x squared minus 13 to the 4th times the derivative of that. That'd be 2x. The 2 and the 1/2 would cancel out to give us back what we started with. So in this method, it lets us deal with this stuff without having to multiply it out. And again, but it's dealing with chain rule. Next problem, similar. 8x squared times sine of x cubed dx. The thing we want to deal with here, we have a function inside of our integral. That would be the sine. Well, let's do just what's on the inside of that, x to the 3rd. So let's let u equal x to the 3rd, which means du equals 3x squared dx. Well, just like last time, we have an x squared dx, so we can divide by that 3 to be 1/3 du equals x squared dx. Substitute it in. So we have our integral. The 8 can move to the outside, as can the 1/3, so we'll just have 8/3. And then the x dx will become the du. The 3rd was already taken care of. And then we have sine of u. What's the antiderivative for sine of u? We have negative cosine u. So I have negative 8/3 cosine u plus c. Plug back in for u. Negative 8/3 cosine of x to the 3rd plus c. Now remember way back when we were looking at derivatives and chain rule, the stuff inside the trig does not change. We have cosine of x cubed. The derivative was sine of x cubed. Makes sense going backwards too. If the inside doesn't change when we take a derivative, the inside shouldn't change when we take the antiderivative. So we start out with sine of x cubed, we end up with cosine of x cubed. The stuff on the outside changes, but not the stuff on the inside. So those u substitution helps quite a bit. Even when you've been doing it for quite a while, u substitution is still beneficial there. But there are some where after you do a lot of it, you might not have to actually go through the u substitution. But sometimes the u substitution really does come in handy, no matter how many times you do it. An example of that would be tangent of x dx. And so you might be thinking like, wait, I don't even know what to substitute u for. And that's one of the big issues here, because people see tangent of x and they think it's like this is just one thing. I wouldn't want to make x u because that's not going to help. If I make the whole tangent of x u, that's not going to help. But remember that tangent of x is not just one thing. We could rewrite this as sine of x over cosine x dx. Now, it's two things. When you have something like this, what you would want to do for u is you want it to equal the denominator. Let u equal cosine of x. So du equals negative sine x dx. Oh, hey, look, sine x dx. If you made sine u and you'd end up with cosine x, well, that's in the denominator already. That doesn't just go away like this. But here we can replace the sine x dx with the du, with a negative du. And so the cosine is u, so the negative can go to the outside. we'll have negative antiderivative of 1 over u du. 1 over u. What's the antiderivative of 1 over u? Remember, it's one of those ones I told you to be careful with, because it looks like u to the negative 1. And so that add 1, that's u to the 0, divide by the new, divide by 0, so we have u to the 0 divided by 0. No, that one doesn't work that way. Remember, 1 over u is a special one, it's natural log. So we have negative natural log of u plus c. Now, technically, we do need the absolute values here because anything that goes into a natural log has to be positive. The natural log is not defined on the negative numbers. So anytime you end up with a natural log, absolute values. A lot of times it's going to be something squared or something where it's positive anyway. This is not one of those cases because we can plug in our u as cosine of x. So we have negative natural log of cosine of x plus c. So there's one that kind of jumps out at you. The antiderivative tangent is natural log of cosine. Kind of weird, but that's what it is. So this is what we're doing in this section. It's using u substitution so we can take the antiderivatives of even bigger integrals. So, and this is really as far as this is going to get us this year. In Calc BC, you get what's called integration by parts, which deals with the product rule and how to take care of that. But that's not something we deal with in Calc AB. We deal with how to get rid of chain rule, which is just u substitution. And so, if you're interested in the other, though, that would be the end of chapter 6. But this is what we're working with. So keep asking questions, keep working problems, and as always, happy mathing.